All right, what's up, guys? What's up? Section 2.5, angles of a polygon. Day 2, because it is day 2, you really don't need to hear much from me right now. You don't at all. We're going to move on to the next slide in a second. But yeah, I'll just massage angles of a polygon down here. We're looking below us here, we got angles of a polygon written. So just more of the same today, more of the same. And I'm just buying you more time to do some of the problem sets and making sure that you feel like you understand these new formulas, because we got at least 3 formulas last class, and I'm including that all of the exterior angles, one set of an exterior angles of a polygon sums to 360. Even though it's not really a formula, I'm 360, I'm still counting as a formula. So anyways, and I think another formula today I kind of go through, and it's just kind of more of the same. I think we're going to look a little bit more closely at regular polygons. So make sure you know what a regular polygon is as opposed to just a polygon. Right, a regular polygon is more specific than that. And that's actually where we're going to start today. We're going to start with that in terms of how we can get the measure of just one angle of a particular type of a regular polygon. So let's just go into it right now. Let's get started. I'll be there for you. When the rain starts to fall, I'll be there for you. Right. And section 2.5, more of the same. You know, I said more of the same. I think, in fact, I showed you both of these diagrams in the last class. So let's just do with it. Let's roll with it. One thing that we hadn't really talked about very specifically, it may have come up on your last homework, but it's something you can totally do. So I at least want to point out to you guys that, hey, you can totally figure this out, right? Sometimes there's these things that seem kind of obvious, like, oh, I ought to figure that out on my own. But, you know, a teacher's got to go through that with you. That's what I'm trying to do right now. So anyways, one of these two shapes here, let's look at this. What's the difference between these two shapes right here? Well, how many sides does the one on the left have, and how many sides does the one on the right have? What's our n, right? The variable n stands for number of sides. Number of sides on the left looks like 5. And number of sides on the right looks like 5. Okay, interesting. So this first slide here, and second slide actually, is going to be about finding the measure of an interior angle, and, so it says and, right, singular, an interior angle of a regular polygon. How might one do that? So I have a question here, right? We've already looked at these two different shapes right here. Of course, this slide is talking about regular polygons. So you might already know it's what I'm getting to at this one. But anyways, before we talk about finding measure of an interior angle of a regular polygon, I'm just going to ask you this here. Just logically, which one of these pentagons, right, the one on the left here, or the one on the right, which one of these pentagons are we able to determine the measure of an interior angle, or one of its angles? Okay, when you say one of its angles, we mean the interior angles, the interior angles. Well, this one, are we able to get the measurement of one of the angles here, right? Just knowing that it has 5 sides, hey, that means I can figure out what that angle measures, for instance? No, in fact, this one is completely irregular, right? It's not a regular polygon. So this looks like an acute angle. This looks like an obtuse angle, another obtuse angle, right? We have no idea what the angle measurements are. These, you know, if we don't have a protractor, and, you know, if we had a protractor, we wouldn't be able to prove that the angle measurement was exact here, okay? But this one here, we're actually going to be able to prove. So the one on the right's the answer, obviously, but the one on the right, we're going to be able to prove not just that these, so remember, these are both pentagons, so these both have the same sum of interior angles, right? Interior angle sum's the same, because remember, this one on the left here, right, makes up 3, there are 3 triangles, right? If I draw a diagonal here and another diagonal here, I'd have 3 triangles created, and that would represent 540 degrees, right? Because 180 times 3 is 540. And then same thing here too. I draw one diagonal here, another diagonal there. This would be the same thing, that this could be subdivided into 1, 2, 3 triangles, of which has 180 degrees. So again, 540 degrees as the sum of the interior angles. But this one on the right here, we can go one step further than that. I just want to make sure you know that, because it's kind of another theorem that you might see here and there. Your book doesn't give it to you as a theorem, but it's a formula in most textbooks. So I'll at least point it out to you here. So the one on the right, of course, we can figure out what the angle measurement of this is here. Okay, so if this were each, right, if each angle were x degrees, right, x degrees, then you'd have 5 of them, right? 5 of those angles. 5 times x degrees. And what would 5 times x degrees equal? Where would it have to equal? Have to equal 540, right? 540, okay, 540. So if ever your angles are marked as congruent, then you can just assign the same variable to at least represent whatever that angle measurement is here. So we know that the total sum, right? This is the sum of any pentagon. And if it's regular, right? If it's regular, you'll have 5 times whatever each one of the individual angles is measure. So this is each angle times it by 5. That's going to tell you the angle sum, right? Each angle times 5 equals the angle sum. Okay, so divide both sides by 5, and that's going to tell you what each of the angles are here. Okay, so x equals 5 goes into 500 100 times, right? 5 goes into 48 times, so that's 108. So a regular pentagon, there we go. How about that here? So it looks a little obtuse right there. 108 degrees, is that obtuse? Yeah, it is. It's greater than 90. Not super far beyond 90, but just a little bit further than 108 degrees. So these are all 108 degree angles. All right, so just to summarize that, right, how you can get the measurements of each angle of a regular polygon. So if you have a problem here, it'd be like a regular 7gon or a regular dodecagon, right? Tell me what one of the angles is in a regular dodecagon. You're able to figure that out here. So the way you can do that, and the way I just kind of showed you there, step 1, find the sum of all of the angles, right? So you're using that formula from yesterday. What's the formula to get this again? I know that I got 540 to remember the whole idea of the triangles here, but how did I get 540 using a formula, a theorem from yesterday's class? Here you're remembering, right? I'm just trying to give you another class to hopefully remember these formulas a little bit better, because they can be easy to forget, but they're important to know, right? You'll get questions on the SATs about stuff like this. So the formula, right, for the sum of the interior angle sum is n minus 2 times by 180, right? Number of triangles would just be 2 less than the number of sides of a polygon. And if it's regular, you can divide that n minus 2 minus 180 by the number of sides, right? By the number of sides, which is 5 right here. And that's how we got in the last slide. We got 108 degrees for the measure of each angle, okay? So let's commit this down to a formula here, because what we ended up doing here, look, we found step 1. Remember, step 1 to finding this, the degree measurements of any of the angles, right? Or all of the angles, right? Any of the angles can have the same measurement as any one of the other angles if it's regular. Because remember, what are the 2 criteria of a regular polygon? A regular polygon is equilateral. Okay, equilateral doesn't really matter so much in this situation, but it's also equiangular, right? Equiangular. All angles are congruent here. So you need to find what all of the angles sum to, and then just divide by the number of angles that you have. The number of sides will be the same as the number of angles in that polygon right here. So the measure of each interior angle of an equiangular, or, right, so this is beyond just a regular, so an equiangular or a regular, right, because with regular you get equiangular for free. N-gon is n minus 2 times 180 divided by n, and then you're good to go. So 108, right, actually using the formula here is basically doing what we just did, what we just talked through. You get 108 there. What about a regular octagon? Somebody tell me, because you have these things memorized. It's helpful to have the main shapes, meaning like hexagon, octagon, dodecagon, decagon, triangles, having all those regular polygons, those main ones, having all of their interior angles kind of memorized. Who's going to tell me? Who's going to be the first person to tell me? Who can crunch the numbers here? Well, I got to do 8 minus 2, which is 6, times by 180. That's going to tell me how many degrees in total, right, all of our angles sum to. And then I divide by 8. Do that on your calculator? Not super hard. 135 degrees is what you should have gotten for there. 6 times 180, what's 6 times 180? Well, it's 1200 minus 120, so 1080 degrees would be the numerator, and divided by 8, 135. That makes sense, okay? So 135 degrees right here, and all of these, look, all these angles are congruent because this is a regular octagon, right? It makes up a stop sign here, octagon. I'm such a nerd, I try to get my 1.5-year-old daughter to call stop signs octagons. In fact, she doesn't know what a stop sign is, but she calls it an octagon. Then I ask her how many sides it has, and then she doesn't. She like counts out like 5 sides and then stops counting. Anyways, it's really cute. I'll keep going on here. All right, we'll continue onward with a regular hexagon. So, it's helpful to kind of memorize these things. Do you remember how many the interior angles of a pentagon was? What was for the pentagon? Remember that? 108 degrees. What about an interior angle of a regular octagon? 135 degrees. Okay, so it's actually helpful to memorize these things because then you can do these problems very quickly and do things related to them very quickly. Anyways, regular hexagon, that should be an easy one. This is definitely one that you want to memorize to have here. 120 degrees right there. That's the easy one to remember. So remember, it's 4, right? 4 times 180. Number of triangles we have here, right? We have 1, 2, 3, and 4. 1, 2, 3, 4 triangles. So 6, right? 6 is the number of sides. Subtract 2, that's the amount of triangles, times 180, and that's 720. And divide 720 by 6, you get 120 degrees there. So here, boom, is where all the 120 degree angles are, right? We have 6 angles of 120 degrees. That's what gets us to 720 degrees. And regular hexagon, any of the individual angles, the interior angles, that means, measures 120 degrees. All right, moving on. We're a little bit of practice here. And taking things a step or two a little bit more difficult is I'm going to start by giving you the angle measurement. So each angle in a regular polygon measures 160 degrees. So you have the individual angle measurement. First of all, is 160 degrees bigger or smaller than all of the angle measurements we've seen so far? So think back to the last slide. We saw a pentagon, we saw a hexagon, and we saw an octagon. All those angle measurements, were they smaller than 160 or are they greater than 160? Think about that. What does that mean about the number of sides that this polygon must have if this 160 degrees is bigger, for instance, than the octagon and the hexagon and pentagon? It's just one thing to consider to make sure your answer, when you eventually get it, does it make sense, right? Does it make sense? So how many sides does it have? Use that formula, right? Use that formula that I had in the last slide, this one right here, and then you already know what this formula is equal to, right? We have the interior angle of 160. You just need to solve for what variable? You need to solve for n. Ready, set, go. You guys got 30 seconds, then I'm going over the answer. Ready, set, go. You guys got this.
And I am not throwing away my shot. I am not throwing away my shot. Hey, yo, I'm just like my country. I'm young, scrappy, and hungry, and I'm not throwing away my shot. I am not throwing away my shot. I am not throwing away my shot. Hey, yo, I'm just like my country. I'm young, scrappy,
I know you can do it. I know you can do it. Let's do it.
It's time to take a shot.
I dream of life without a monarchy.
All right, 10 seconds.
Unrest in France will lead to anarchy. Anarchy. How you say? Anarchy.
5, 4, it's okay if you pause. 3, 2, and 1. All right, let's go over it. So remember, you already know what the angle measurement is. One interior angle is given to you as 160 degrees equals the amounts, right? The top represents the amount of in total of degree measurement of the sum of all the interior angles, and then you just divide by the number of interior angles you have, and that's going to tell you what the measure of one interior angle is. So this is your known here. You know this, know the angle measurement. Your unknown is just what is the number of sides. Got to solve for it. Okay, so this gets a little bit tricky algebra-wise. Not everybody is going to solve this super easily, but because here we have n in the numerator and we have n in the denominator. Question: how do we get it so we don't have n in both the numerator and the denominator? What can I possibly do to say, maybe get rid of this dividing by n? I could multiply both sides by n. If I multiply both sides by n, this n would cancel out. So if I multiply this side by n and this side by n, then n divided by n would be 1, right? It would be 1. So it would go away, okay? And then at that point, I'd have 160n over here, right? 160n over here. This did a little bit more work too, where we multiply both sides by n, and then it looks like we did the distributive property here, where we distributed 180 times n is 180n, and 180 times -2 is -360, okay? So remember, distribution could work from the 180 could have been over here and distributed in, or the 180 could have been over here, because order doesn't matter when it comes to one expression multiplied to another expression. So it's the distributive property of multiplication over addition, so it goes to both the n and it goes to the -2. And this is why I see this right here. Okie dokie, we have 180 n's here and 160 n's here. Subtract 160 n from both sides. And, it looks like we did this here. Looks like we subtracted 180 n from both sides, right? 180 n. So we did 160 n, subtract 180 n, and then we have -20 n on this side here. So what do I got to do? I'm going to solve for 1 n. Divide both sides by what? Divide them both by -20, okay? So -360 divided by -20 is 18. And there we have it. The polygon has 18 sides. And there it is right there, folks. There it is. Let me show a little bit more of the work in case you want to go a little bit more slowly here. Again, right, we got to be careful with the algebra stuff here because, I know you mostly as geometry students than algebra students here. Okay, so this is what I did here. Multiply both sides by n. N divided by n is a 1. So the n doesn't actually end up multiplying to this because it canceled out here. And then I distribute it here. Right, 180 times -2 is -360, and 180 times n is 180n. So that's what I had, and then subtracted 180n from both sides. And we see this here, 160n minus 180n, right? We're taking away more n's than we have, and 20 more, right? So we end up with -20 right here. Divide both sides by -20, right? Undoing everything that's kind of happening to get us there, and -360 divided by -20 is 18, right? 36 divided by 2 is 18, so it kind of makes sense. Anyways, this has 18 sides, so this kind of makes sense because your 8s, right? So remember that what you saw on the last slide is that a pentagon, a regular pentagon, had a 108-degree angle, single angle. A regular hexagon had a 120-degree angle. A regular octagon had a 135-degree angle. Do I know what how many sides get 160 degrees? No, I don't. I don't have that one memorized, but it would make sense that 160 degrees, that's bigger than 135, bigger than 120, bigger than 108. So the more sides a regular polygon has, the larger this angle is going to be. So it makes sense that this would have more than 8 sides, for instance, which was 135 degrees. And 160 is quite a bit bigger than 135. It's closer to 180, right? It's closer to the maximum angle than it is 135. So 18 sides, the more sides we have, the larger the angle will be. And what does this actually look like? This actually come up very, very important to us in chapter 7, which is circles. What does this look like? Yeah, it looks like a circle. I just said it here. So the regular polygon, the more sides it has, the closer it's actually going to appear to a circle. It'll eventually get a lot of the properties of circles. And this kind of looks like the radius of a circle, doesn't it? Anyways, we'll get to that all in chapter 7. All right. I think we're actually almost done. I just got kind of like a summary slide for section 2.5 in a second. Sometimes it's just nicer when we get to spend all this extra time on this stuff. So make sure we totally get it and buy you time to ask questions, because you definitely have to ask questions in this stuff. That's really the way you get better. Question yourselves, practice it. You got this, okay? So here, what this slide's about is comparing interior angles to the exterior angles of a regular polygon. So I just want to point this out because I know we've talked a bit about exterior angles, but it helps because interior angles super related to exterior angles. I know we only have that 360-degree thing when it comes to exterior angles, but how can interior angles actually help us get the exterior angle of a regular polygon? Okay, so I filled this in here. This is a regular hexagon. So we know, because we just did this a few slides ago, that each angle of a regular hexagon measures 120 degrees. Okay, so if each interior angle measures 120 degrees, if you got asked the question, what is the measure of one exterior angle of a regular polygon? The answer to that's pretty simple because you're looking at a diagram, but what would you have to do? You would just have to find what the supplementary angle is of this 120 degree angle, right? Because an exterior angle is part, right? This is the exterior angle right here, right? Right here is an exterior angle. We extended one of the sides, and the extension taken with the adjacent sides this here, that angle would fit the definition of an exterior angle. So an exterior angle is simply supplementary to one of the interior angles. So we get 60 degrees here. Okay, and can this be said for every exterior angle? Let's check it out. I just drew that in. Yes, we can. Yes, 60 degrees, of course, because it's supplementary to the interior angle. And we can go all the way around. And of course, in single exterior angle of a regular polygon equals 60 degrees, equals 60 degrees. And look at these numbers here. I put in all these 60 degrees right here, 60 degrees right here. So 60 plus 60 plus 60. Why does it make sense that actually all of these angles would be 60? Obviously, it's supplementary to 120, but what's another thing when we double check, does our answer make sense? What does this actually match? What does this help us think about? Okay, well, you looked at one set. Let's go back here. You looked at one set of the exterior angles, because as we go around by direction, right? We keep extending to get exterior angles. We found one set of 6 exterior angles. And what do they all sum to? Well, they all sum to what? They sum to 360 degrees, okay? So as a reminder, another reason why I go through this is because in case you forgot this one from last class, and you should know it going forward, right? Definitely, you would definitely have to use this one here. As a reminder, the sum of the measures of a set of exterior angles, that means kind of going in one direction, right? Because we could argue that this right, if I extended this right here, that would be an exterior angle, but no, then I'd be going in 2 directions. I'd be going this way too. So in both directions, like just one direction, kind of one direction, the angles sum to 360 degrees. And then the other direction, they also sum to 360 degrees. And this makes sense here, right? That at a single exterior angle of a regular hexagon, 60, well, they have 6 of them in one direction. So 60 degrees times 6 would equal 360 degrees. So it actually matches the theorem that I shared with you guys last class. Okay, so let's generalize this here because there's actually another theorem that I want you guys to commit to using because it's actually a really easy theorem. You could have, right? You might have been thinking, Mr. Fortin, you're working too hard because if you're asking what is the measure of one exterior angle of a regular hexagon, there was actually an easier way to figuring this out rather than thinking about, well, what is the interior angle and then what is the supplement of the interior angle. Okay, so that's one way of getting the answer. So if you say started from scratch, what is the exterior angle of a regular hexagon? You could have done, well, I got to find my interior angle. So that's n minus 2. So, okay, so 6 minus 2, which is 4, times 180, which is 720, divide by 6. Listen how many steps I'm doing here. So divide by 6, and that's 120 degrees. And then I got to take 120 degrees away from 180 because I know that my exterior angle is supplementary to the interior angle, and the answer is 60. That was a lot of work. What was an easier way to get there, though? How would I know for sure, right? For sure that my exterior angle were 60 because there's a lot easier way to do it. Well, you could work backward from knowing what is the sum of all of these, of all 6 of these exterior angles going to be, right? Well, the exterior angles of any polygon is 360 degrees. And because you have 6 of them, because this is a hexagon, you have 6 exterior angles in one direction, you just need to divide that 360 by 6 in order to get one of the individual exterior angles of a regular polygon here. Okay, so generalizing this, how many exterior angles in one direction would a heptagon have? It would have 7, so I would have to do 360 divided by 7 to get the measure of one exterior angle of a regular heptagon, right? What about an octagon? Okay, they'd have 8 exterior angles in one direction. So to get the exterior angle of a regular octagon, I would just have to take 360 because I know the sum of all the exterior angles in one direction would sum to 360, and then I'd have 8 of those, so I divide that by 8, and I would get 45 degrees for the measure of one exterior angle of an octagon. So it's very easy, and then you can always double check it against what the interior angle is. So for instance, the octagon interior angle measure for a regular octagon is 135 degrees, right? So 360 divided by 8 is 45. So 45 is supplementary to 135. We've checked our answers. We know we're good. Okay, so I just blabbered on about that quite a bit. Hopefully you got what you need to do out of it. Probably said a little bit too much. Okay, so that was kind of the big thing here. They got more just kind of review, and then I'm going to do a summary slide at the end. It'll be A-okay, good to go. Good to go, start on the homework, and feel like you're still hopefully rocking out on the stuff. You're doing pretty well. Exterior angles of polygons, just want to remind you again here too, in case it's been confusing. I'm trying to show it to you in different ways, and maybe it makes sense one way, and that's the way that I'm happy with. Whatever makes sense to you is the way that I'm happy with. And other people respond to some slides differently than other slides, so I'm just showing it again here. Anyways, just to remind you, the exterior angles of polygons, they come in sets, and all are in the same direction from the extension, okay? Extend this way, move onward. Extend that way, move to the next side. Extend that way, extend that way. And you have 4. Okay, so when we're talking about this, 1, 2, 3, 4, that sums to 360, okay? Obtuse, acute, right? It kind of makes sense they extend to 130, okay? You can't extend in the other direction. Notice here, this one's already extending this way, already extend that way, already extend that way, already extend that way. You can't also extend it this way and say, call this this is still an exterior angle, but it's part of a different set. So if I extend here, I extend here, and extend here, those other angles that get created are part of the other set here, okay? So those 4 that I just tried to point at would also add to 360, okay? But it's not part of the same exterior angle set. The amount of exterior angles you have in a given n-gon is twice as much as the number of sides. So this quadrilateral would have 8 exterior angles, because it would be 4 angles as part of each set. But anyways, we don't need to worry about that now. And just to point this out here too, this looks like an exterior angle, right? It does. It's in the exterior of the actual shape. I know I explained this a couple lessons ago, but in case you missed it, right? This up here, it looks like it's in the exterior. This is the interior of the quadrilateral. That's in the exterior, but this is not an exterior angle. It doesn't fit the definition of an exterior angle. This is just simply a vertical angle, right? A vertical angle of the interior angle, so it would have the same measurement. Just worth pointing it out. Okay, so just a reminder on this. I know that I started my lecture last class, section 2.5, discussing this theorem, because a lot of people forget this one, oddly enough. And it's an easy theorem, right? So I wanted to both start the section talking about this theorem and finish the section talking about this theorem. And we're not going to go through the proof of this one, because it is fairly obvious. It's fairly obvious to understand it, right? Understand this formula. Without proving it, and the proof gets a little bit messy, even though it makes sense. So let's just avoid it. I think we'll be better there. And finally, this is it. So I didn't actually have a homework slide. No homework slide. You're still gonna have homework. Just check Google Classroom or wherever I'm posting it. But this is my last slide for today. Normally it's homework, and it's this one today. And it's just kind of a summary of this section, because this was a very important section, right? These are some formulas you should definitely know, and figured I'd just get them into one place in case kind of my lecture and discussion through all of it got kind of messy and you had trouble finding everything. There you go. There are the 4 formulas you need to know from this section. How do I get the sum of all angles, interior angles of any polygon? What about the angle sum of one set of the exterior angles of any polygon? Okay, that's just gonna be 360. Okay, and n minus 2 times 180. That was kind of the big one. That's all the sum. Like you add them all, take all those interior angles, add all their measurements up, you get 360 less than 180 times the number of sides. But just remember the formula. That's better than listening to me right here. Anyways, just got to divide it by the number of sides to figure out one interior angle of a regular polygon. Okay, so remember that formula is just for a regular polygon. So a common question I might ask, or standardized tests ask, or other teachers ask is, tell me what an interior angle is of an octagon. And then the answer is, well, there's not enough information to conclude, right? Because you didn't say what? You didn't say if it was regular or not, or equiangular or not. So anyways, you got to be on the lookout for this. If it's asking you exterior angle, a specific exterior angle of a particular polygon, it needs to say regular or equiangular for you to use this formula, right? This formula, or this formula if you're trying to get the interior angle. Okay, so make sure you have these 4 formulas and have them committed. I hope you learn them when we do the homework problem sets, and you learn them and you're ready to go for the tests here. And finally, these were the key definitions in case you had trouble remembering. There's kind of a lot of stuff in this section, and this is just a second day to kind of take a deep breath and feel like, hey, hopefully I got this. And it's I know we move quickly. It might feel like we move slowly in some areas, but that's okay too sometimes, because sometimes we feel like we move quickly, and other times we just have to have these sections where we can sort of collect ourselves and take a deep breath. And I hope this was one of those sections for you here. Okay, make sure you know what a polygon is, right? Definition of a polygon, and then a more specific type of polygon is convex polygon. Those are most of the polygons we study in this course here. And then, of course, a regular polygon, both equiangular and equilateral polygon. And one thing that I didn't formally define out for you, sometimes it's tough for me, guys, to be like, I'm going to spend time in class being like, here is this definition, okay? Because a lot of these definitions are pretty obvious. They're obvious, but I still need to tell them to you. So sometimes I'll wait a little while, after you kind of been working with them, to be like, oh, hey, this is actually a definition that we should talk about, right? We should talk about in case, just so you don't miss it here, okay? So a diagonal, right? I haven't defined this yet, so make sure you put this in your notes. A diagonal is a segment of a figure, right? A segment of a polygon specifically, right? A segment that joins 2 non-consecutive vertices of a polygon, Okay, so a diagonal, actually, I said it kind of misleading a second ago. A diagonal, these diagonals here are in red. A diagonal is not part of a polygon. Who can tell me why a diagonal wouldn't be considered part of this pentagon? Well, a pentagon, remember, any polygon is formed as the intersections and the segments, of course, are formed by segments. So we lay out segments, and then the segments we see here is the actual polygon here, okay? So your diagonals don't include these segments, or they're not part of these segments here, except for the endpoints, right? The endpoints of the diagonals will be the vertices of the polygon, okay? So if you can draw a line segment from one vertex to another vertex of a polygon, and it is not a side of the polygon, then it's a diagonal here, okay? So it's a segment joining two non-consecutive vertices of a polygon. So obviously ED isn't a diagonal because that's a side, but we can go, if E doesn't go to C in the polygon, right? We take a detour to D and then back to C, so these are two sides here. EC is a diagonal, and EB is a diagonal because E and B do not have a segment in common. It's actually part of the polygon, okay? So those are diagonals, and those will be stuff we'll be doing all year. All right, and with that, right, that lecture could have probably done twice as fast, or I could have talked half as much, but still, this wasn't as long as a lot of the other ones are. But hey, sometimes it helps you go slow. And again, take that deep breath. You're doing great. Give the homework a shot. Email me if you have any questions, and we'll of course be ready to review sometime soon. Take care, guys.
Everybody